if I told you that the vibrant yellow of that lemon sitting on your kitchen counter right now doesn't actually exist in the physical universe, you'd probably call me crazy.
I mean, it does sound completely absurd when you first hear it.
Right. But by the end of our conversation today, you're going to realize that almost everything you think you know about the light hitting your eyes at this very second is, well, it's a complete biological illusion.
It really is. And, we rely on light for every waking moment of our lives.
Exactly. You use it to navigate your house, you feel its warmth on your skin, you gaze up at distant stars. It's just so utterly ordinary that we completely take it for granted.
We do. But the moment you actually stop and try to pull that everyday illumination apart, when you try to figure out what a beam of light is actually made of, the whole concept of reality just starts to fracture.
It really broke the minds of the greatest scientists in history. So welcome to today's deep dive, everyone. Our mission today is exploring a really fascinating excerpt titled, "Here is Something You Have Never Once Thought About." And it uses light to unravel our fundamental understanding of reality.
Yeah, because answering that single, seemingly basic question of what light is, it caused one of the most intense, productive, and frankly bizarre arguments in the history of physics.
So to really wrap our heads around this, we have to look at the only two logical guesses early scientists had on the table.
Right. And these two guesses seemed completely mutually exclusive. So back in the late 1600s, Isaac Newton argued that light was a stream of tiny physical particles.
Yeah.
He said, imagine microscopic, invisible bullets being fired out of a candle or the sun, traveling in perfectly straight lines and physically bouncing off whatever they hit.
I mean, that makes complete intuitive sense. If I picture light as like firing tiny bullets from a BB gun, it perfectly explains a lot of what we see every day.
Oh, absolutely.
Like, it explains why light casts sharp, defined shadows when an object blocks those bullets. And it explains mirrors, too.
Yes, the reflection angle.
Right. If you bounce a rubber ball off a brick wall at an angle, it bounces off at that exact matching angle. Light does the exact same thing when it hits a mirror. So, Newton's particle theory feels incredibly solid. It aligns with the physical, macroscopic world we actually interact with.
It does. And he wasn't just resting on his massive reputation either. The mathematics of optics actually backed him up. That is, until a Dutch physicist named Christian Huygens pointed out a pretty glaring flaw.
Uh-oh. Enter the challenger.
Exactly. Huygens proposed that light is not a particle at all, but a wave, like a ripple traveling through some invisible medium.
So very similar to how sound is a ripple moving through the air or a swell moving across the ocean.
Precisely. Huygens had observed phenomena that Newton's tiny bullets simply could not explain.
Wait, like what? What could a wave explain that a tiny little bullet couldn't?
Well, think about that classic broken straw optical illusion. When you look at a straw resting in a half-full glass of water.
Oh, right, yeah. The portion of the straw in the air looks perfectly straight, but the moment it hits the water line, it looks completely disconnected.
Right. It looks bent at a sharp angle. And that happens because light literally bends as it passes from the medium of air into the denser medium of water.
Oh, I see. Because if light were just tiny bullets flying in straight lines, they would just shoot straight into the water without magically veering off course.
Exactly. Bullets don't just abruptly change their angle because they hit water, but a wave slows down and changes direction when it hits a denser medium.
Okay, so you have these two heavyweights, particles on one side, waves on the other. And because Newton had such a massive, untouchable reputation, my understanding from the source materials that the particle picture essentially won out by default for about a century.
Pretty much, yeah. People didn't really want to argue with Isaac Newton.
I mean, fair enough. But science relies on pushing past assumptions and demanding proof. So how did they finally settle a debate this massive?
They actually settled it in 1801 with an experiment so elegant you could practically recreate it on your kitchen table today.
Really?
Yeah. An English polymath named Thomas Young devised what is now famous as the double-slit experiment.
Okay, the double-slit experiment. Walk me through it.
So he took a solid barrier, cut two incredibly narrow, closely spaced slits right into the middle of it, and shone a beam of light directly at those slits.
And then what?
Then he simply observed the pattern that the light made when it hit a blank screen placed behind the barrier.
Well, if we assume Newton is right, and light is made of solid little bullets, shouldn't you just get two bright stripes on the back screen?
That would be the logical assumption, yes.
Yeah, it's like taking a can of spray paint and spraying it at a piece of cardboard with two slits cut in it. You'd just get two lines of paint on the wall behind it. The paint particles go through the holes or they hit the cardboard. That should be the end of the story.
That is precisely what you would expect from particles. But when Thomas Young actually looked at the screen, he didn't see two crisp lines. He saw a whole series of bright and dark bands spreading out completely across the width of the screen.
Wait, really? A whole series?
Yeah, an intricate, repeating pattern of light, dark, light, dark. He was looking at an interference pattern.
Okay, let's unpack this because that is wild.
Yeah.
So if we use the analogy of dropping two heavy stones into a completely still pond at the exact same time, right? Just a few feet apart.
That's a great way to visualize it.
Each stone creates a set of circular ripples spreading outward. And eventually, those two sets of expanding ripples crash into each other. When they overlap, they interfere.
Exactly. They interact with each other's energy.
Right. So if the high point, like the crest of one ripple, perfectly meets the crest of another ripple, they add together to make a super ripple, a much bigger wave.
Yeah.
But if the crest of one wave meets the low point, the trough of the other wave, they just cancel each other out completely. The water just stays flat.
You nailed it. And that is exactly what Young was seeing with the light.
So you're saying that the light emerging from those two slits was acting like the water ripples. Where the light waves reinforced each other, they created a bright band on the wall.
Yeah.
And where they canceled each other out, they left a dark shadow.
That's it. Exactly.
And because physical bullets absolutely cannot cancel each other out into nothingness in midair, light absolutely had to be a wave.
The conclusion seemed completely unavoidable. And, it received a massive mathematical boost a few decades later in the 1860s.
Oh, this is the Maxwell part, right?
Yes. A brilliant Scottish physicist named James Clerk Maxwell was working out the mathematics of electricity and magnetism. At the time, everybody thought those were completely separate forces.
Right, like static shock versus a fridge magnet.
Exactly. But Maxwell unified them into a single set of equations. And in doing so, he discovered that his math predicted the existence of waves, specifically waves made of electric and magnetic fields that basically feed off of each other to keep moving forward.
Can we define that really quickly? Because an electromagnetic wave is a pretty foundational concept for this whole deep dive.
Of course. So, an electromagnetic wave is a self-sustaining ripple of energy. Unlike ocean waves that physically need water, or sound waves that need air to travel through, an electromagnetic wave needs no physical medium at all.
So it can travel through the absolute empty vacuum of deep space.
Exactly. And when Maxwell calculated exactly how fast these theoretical electromagnetic waves should move, the number that dropped out of his equations was a massive shock.
Is the speed of light, wasn't it?
It was precisely the known speed of light.
Why was that specific number dropping out of the equation such a bombshell for physicists?
Well, imagine doing a really complex mathematical equation to figure out the maximum speed a new sports car can drive, and the answer comes out to precisely the speed of sound.
Oh, wow. Okay.
Right. You would instantly know that the mechanics of the car and the physics of sound must be deeply, fundamentally connected. So when Maxwell saw the speed of light emerge from equations that were supposed to be just about magnets and static electricity, he realized light wasn't just some random wave.
Light was an electromagnetic wave.
Exactly. Case closed.
Except the universe is never that simple, is it?
No, it really isn't.
Just when the physics community thought they had it all figured out, reality totally refused to cooperate. Moving into the late 1800s and early 1900s, things just started to break. Two new experiments popped up that entirely defied the wave theory.
Yeah, and science often advances not through sudden brilliant ideas, but through things simply failing to work the way they are supposed to.
So what was the first failure?
The first major failure involved glowing hot objects. The wave theory made a very confident mathematical prediction about the colors of light that a glowing hot object should emit.
Like a piece of iron in a blacksmith's forge.
Exactly like that, but that prediction was catastrophically wrong compared to real-life measurements in the lab. The math just did not match reality. So in 1900, a German physicist named Max Planck sat down to fix the math.
And how did he fix it?
Well, he found he could only make the equations match reality by assuming something that, to him, seemed completely absurd. He had to assume that light energy isn't a continuous, smooth flow like a river. Instead, it comes in discrete, individual lumps.
Hold on, what do you mean by a lump of energy? I mean, energy isn't a physical object you can hold in your hand. How can it be lumpy?
It is a really counterintuitive concept. We call this quantization.
Okay.
Think of the difference between walking up a smooth ramp versus walking up a flight of stairs.
Okay, I'm with you.
On a ramp, you can stop at any possible height you want. It's totally continuous. But on a staircase, You can only stand on step 1 or step 2. You cannot stand on step 1.5.
Right, you just fall down to step 1.
Exactly. Planck's math suggested that light energy operates like the stairs. It can only be emitted or absorbed in specific, strictly defined, indivisible chunks. He called one of these chunks a quantum.
So he essentially broke this smooth, flowing wave into tiny, choppy staircase steps.
He did, but Planck didn't even think these quantas were physically real. He thought he had just invented a clever mathematical trick to make his equations balance on paper.
But he was wrong about it being just a trick, yeah.
Oh, completely wrong. And the second problem proved him wrong. It had to do with something called the photoelectric effect.
Which is the foundational science behind the modern solar panels on people's roofs today, if I remember the source right.
Yes, exactly. The basic principle is that if you shine light onto certain metals, the metal will physically spit out electrons.
But wait, if light is a continuous wave of energy flowing like water, a dim light shining on that metal for a long period of time should eventually build up enough energy to knock an electron loose, right? Like gentle waves slowly eroding a piece of a beach over time.
That makes perfect sense under wave theory.
Or, if you use a super bright red light, that massive towering wave of energy should easily blast electrons out of the metal immediately.
Both of those are completely logical wave theory predictions, and they both fail completely in reality.
Really?
If you shine a red light on this metal, no electrons come out. It doesn't matter how blindingly bright you make that red light, and it doesn't matter if you leave it shining for 10 straight years. 0 electrons.
Wow.
But if you switch to a blue light, electrons pop out instantly, even if that blue light is incredibly faint and dim.
Which completely shatters the idea that it's just a wave of energy slowly washing over the metal.
Completely shatters it.
And this is where Albert Einstein enters the picture in 1905, right? And actually wins his Nobel Prize for this.
He did. Einstein looked at this failure and realized that Planck's mathematical trick wasn't a trick at all. Light truly does arrive in physical, discrete packets of energy. Today, we define these individual packets of light as photons.
Okay, photons.
Yeah. And Einstein's realization completely solves the photoelectric effect puzzle.
So how does a photon explain why the dim blue light works, but the bright red light doesn't?
Well, the best way to visualize what is happening on the surface of that metal is to think of a very stubborn vending machine.
Okay, a vending machine.
Imagine a vending machine that dispenses a snack, and the snack represents freeing an electron from the metal. This machine is exceptionally strict. It only accepts $1 coins.
No bills?
No bills, no smaller change, only single $1 coins. Knocking out an electron is a strict one-on-one collision. So a high-energy blue photon is exactly like a $1 coin. If you put it in, you instantly get the snack. The electron is freed.
Wait, let me make sure I get this analogy. A red photon has a longer wavelength, so it's a lower energy photon. In this vending machine analogy, the red photon is like a penny.
Exactly, it's just a penny. So if you shine a blindingly bright red light on the metal, you are essentially dumping a roaring torrent of 10 million pennies into the vending machine all at once.
But the machine only takes dollar coins.
Right. It doesn't matter that 10 million pennies technically hold a lot of value collectively. The machine rejects every single one of them. Nothing happens.
That is brilliant. So Einstein proved that brightness is simply the number of photons hitting the metal. Brightness doesn't change how much energy each individual photon carries. Light behaves exactly like a localized physical particle.
It does.
But here's where it gets really interesting, because this creates a massive, seemingly impossible contradiction in physics.
A huge contradiction.
Right, because Thomas Young's double-slit experiment definitively proved that light is a spread-out ripple that interferes with itself. But Einstein's explanation of the photoelectric effect definitively proved that light is a localized bullet, a photon, that hits one single electron at a time. How can it possibly be both?
Well, physicists didn't just throw their hands up in defeat, though I'm sure they wanted to. They actually combined the experiment.
Oh, this is so cool.
Yeah, they went back to Thomas Young's double-slit setup, but this time with highly advanced modern technology. They turned the light source down so incredibly low that the laser was only firing one single photon at a time toward the barrier with the 2 slits.
Firing a single packet of light. So what happens when that solitary photon hits the back wall?
It crosses the barrier and lands on the back screen as a single, tiny, precise dot. One localized particle makes one localized dot. You fire a second photon a minute later, you get a second distinct dot on the screen.
And if you stop the experiment right there, it looks perfectly aligned with Newton's tiny bullets.
Exactly.
But the physicists don't stop there. They let the machine run. They let millions of these individual solitary dots accumulate on the screen over hours and hours. And as the dots build up, they don't just form two stripes behind the two slits. Dot by individual dot, they slowly build the exact same wave interference pattern.
It's mind-blowing.
That repeating pattern of light and dark bands, how is that even possible if the photons are traveling completely alone?
I know. It forces us to accept a concept that entirely defies human logic. Because each individual photon went through the entire apparatus completely alone, there were no other photons around for it to crash into or interfere with.
Right.
So the only way the math and the physics make sense is if we accept that a single photon doesn't travel through space like a tiny baseball. It travels as a wave of possibility.
A wave of possibility.
Yes. It essentially goes through both slits simultaneously, interferes with itself as a wave, and then only collapses to land as a single definitive particle at a spot on the screen where the wave's mathematical probability allows it to.
It goes through both slits at once. That alone is deeply unsettling. But to me, the most disturbing part of all of this is what happens when scientists try to cheat.
Oh, you mean the detector?
Yeah. When they say, we don't believe a single particle goes through both slits, we're going to put a tiny detector right at the slits to simply look and measure exactly which slit the single photon actually goes through.
Yeah, and the result of that is terrifying. The moment you place a detector there to watch the slits, the interference pattern completely vanishes on the back screen.
It just disappears.
Mm-hmm.
You put a camera there to watch it, and the photons suddenly stop acting like a wave. They abandon the complex pattern and just form two boring stripes on the back screen, exactly like the spray paint analogy from earlier.
They do.
The simple act of trying to measure its path forces the photon to choose a definite route. By looking at it, you fundamentally change the physical outcome of the experiment. This is known in quantum mechanics as the observer effect.
And this is where physics crosses over into deep existential philosophical dread. Einstein himself absolutely hated this implication. He famously asked a colleague if he truly believed the moon did not exist when no one was looking at it.
It really makes you wonder.
Yeah.
But we have to clarify what observation means here, right? Because it's a major point of confusion for people learning this.
It is a massive point of confusion.
Yes. How does a photon actually know it's being watched? Does it have a microscopic brain?
Not at all, no. See, in the macroscopic world, you can observe a car driving down the street entirely passively. The ambient light bounces off the car and hits your eye, and the car's momentum is entirely unaffected by you looking at it.
Sure.
But in the quantum realm, things are so unfathomably tiny that you cannot passively observe them. To quote-unquote look at a photon passing through a slit, you have to bounce another particle off of it. You have to physically interact with it to measure it.
Oh, I see.
And that physical interaction is what causes the delicate wave of possibility to collapse into a definite state. The universe, at its absolute finest, most fundamental grain, behaves in ways that are entirely alien to the macroscopic world our brains evolved to understand.
That makes a lot of sense.
Because our ancestors evolved to track animals, find fruit, and avoid predators, you know? We did not evolve to intuitively grasp a reality where particles exist in states of probability until they are interacted with.
Wow. Okay, but if particles are fundamentally changing their behavior just because they interact with something, what does that mean for the normal macroscopic world? After diving into the deep end of quantum dread, I feel like we really need to pull this back down to human scale.
I agree. Let's ground it.
What about the light in the room I'm sitting in right now?
Let's bring it back to the electromagnetic spectrum. We need to introduce a measurement scale here. The nanometer.
Okay, a nanometer.
A nanometer is unimaginably small. It is 1/1,000,000th of a single millimeter.
That is tiny.
Extremely. And visible light, which is the light our human eyes can actually detect, exists only in a tiny, restricted band of wavelengths, measuring just a few hundred nanometers wide. In this visible band, red light has the longest, most stretched-out wavelength that our retinas can register. Violet light has the shortest, most compressed wavelength.
I've always loved comparing human vision to sitting at a piano keyboard.
Oh, that's a good one.
Yeah, imagine a grand piano keyboard that stretches for miles and miles in both directions.
Yeah.
The visible light we can see, all the rich colors of the rainbow, represents just one single octave on that endless piano. Our eyes are entirely blind to the vast majority of the instrument.
That is a phenomenal way to visualize it. The rest of that keyboard is vast, and it actually surrounds you constantly.
Really?
Yeah. If you take a wave of light and stretch its wavelength longer than red, moving out of our visible octave, you get infrared light. You can't see it, but your skin feels it as radiant heat.
Oh, like a heat lamp?
Exactly. Stretch it even longer, and you hit microwaves and then radio waves, which can be meters or even kilometers long.
Wow.
And on the other end of the keyboard, if you squeeze the wavelength shorter than violet, you get ultraviolet light, which is the unseen light that gives you a sunburn. Squeeze it shorter still, and you get X-rays and finally gamma rays.
So we are effectively blind to 99% of the light in the universe.
We are. The crucial thing to understand here is that from a local FM radio broadcast to the X-ray machine at the dentist's office to the glow of your cell phone screen, they are all exactly the same thing.
They're all just photons.
They are all photons. They're all electromagnetic waves. They differ only in how tightly compressed their waves are and therefore how much energy those quantum packets carry.
So what does this all mean for our day-to-day experience? When we talk about this tiny slice of visible light, it completely changes how we understand the objects around us. Let's go back to that simple yellow lemon sitting on the counter from the intro.
Let's do it.
Sunlight is a chaotic mixture of all the visible wavelengths, all the colors blended together. When sunlight hits that lemon, the physical matter of the lemon's skin absorbs most of those wavelengths. It absorbs the red photons, the blue photons, the green photons, but it reflects a very specific band of wavelengths back outward into the room.
And this is exactly where physics hands the baton over to biology. Those specific reflected photons travel through the air, enter your pupil, and strike specialized cone cells on your retina that are biologically tuned to react to that exact wavelength.
Okay?
Those cells fire off electrical signals into your optic nerve, which zip into the visual cortex of your brain, and your brain interprets that specific electrical signal as the vibrant concept we call yellow.
So the yellowness does not actually exist in the lemon itself. The lemon is just a bunch of atoms absorbing and reflecting energy. And the yellowness certainly doesn't exist in the photon either. The photon is just a vibrating, colorless packet of electromagnetic energy.
Color is completely constructed. The vibrant yellow of a lemon, the deep blue of the sky, the alarming red of a stop sign, they are all illusions entirely fabricated inside your brain. It is basically an evolutionary user interface designed to help you navigate a world of radiation.
It is incredibly humbling. As we wrap up this deep dive, I want you to really think about this. The next time you walk into a dark room and flick on a simple desk lamp, you aren't just illuminating a space, you are actively unleashing a flood of quantum anomalies.
It's quite a picture.
You are releasing trillions of packets of electromagnetic energy that exist in a bizarre state of pure possibility, rippling through the room as waves, completely devoid of color until they crash into your retinas. The most ordinary, mundane sight in your house is running on mechanics that reveal reality is infinitely stranger than it appears on the surface.
Which leaves us with one final, lingering thought to explore on your own.
Oh, lay it on us.
We've established that the vivid color of a lemon is a biological fabrication. The universe doesn't possess color, only invisible wavelengths.
Right.
And we've established the observer effect. The physical interaction of measuring a single photon forces it to abandon its fluid wave-like state of possibility and collapse into a hard-defined particle. So if the qualities we see are just subjective biological illusions, and if interacting with quantum particles fundamentally changes how they exist in space, does the physical universe even have a defined objective state when a conscious observer isn't there to interact with it?